today by Ingo, Ab-initio approaches to nuclear system and applications. Okay, thank you, Ingo, for coming, and now play the game with the students.
Sure. So thank you very much for inviting me, and welcome everybody to my lecture. I was charged to talk about the Ab-initio approach to nuclear physics and its applications to dense matter and astrophysics. And just for my own curiosity, by show of hands, who of you works in Ab-initio nuclear theory, or would say they do work in Ab-initio nuclear theory? Okay, 2 hands I see. Okay, great. Then I have a lot to cover. This doesn't work, sorry. So, okay. Perfect. So I will talk about many things if I get to it. There are several topics I want to cover. First, I want to give you a general introduction to nuclear forces coming from a very short QCD background, talking about general constraints on nuclear interaction, two-nucleon scattering and phase shifts, and then talk about the more historic approach, which is phenomenological nuclear forces, and you will hear about what that means. Then I talk about a big topic called chiral effective field theory, which is the modern approach to nuclear forces, talking about the general principles, power counting, 2 and 3 body forces, how we construct these interactions and what we fit them to, basically. I will show some results and then talk about quantifying uncertainties. And then, there's even more. I will talk about nucleonic matter. So if we put many nucleons in a system, like in a fluid, a dense fluid of nucleons, how can we describe this? How can we use the Ab-initio approaches to study this? Basically, I will connect this to chiral EFT and then basically show you some results. And finally, I want to talk about the topic I'm most passionate about, which is neutron stars and multi-messenger observations from neutron stars. But before I start, I have a few requests. The first one is, please ask many questions, and ask right away. You don't want to listen to me talk that long. And if you don't ask, there will be exercises for you. So the more questions you ask, the more we can talk, and I think the more you learn, and the easier it is for me and for you. So I think that's good. So yeah, ask me many questions, ask right away. I have a bias, like everybody does. And so I will focus on topics that I think are important. If you have other questions or want to hear about something else, just let me know. We can address those in the exercises. And if you want to reach me, this is my email address. So just send me an email. Cool. Then let's begin by a general introduction to nuclear forces. And as I said, this is the topic I'm most passionate about. So I start with neutron stars. Neutron stars, I don't know how many of you know about neutron stars. I will talk about them later during these lectures, but they are very dense objects, stellar remnants of supernova explosions of the order of the mass of our sun. And this mass is compressed in a radius of a few 10 kilometers. 10, 12 kilometers. And as you see, sometimes these neutron stars live in binary systems. So come on, restart. So they live in these binary systems. Let's go back. And orbit around each other. And when they orbit around each other, they can radiate gravitational waves, which is what you see coming in here in blue. And so the orbit loses energy. The neutron stars approach each other even more. It loses even more energy. And it's basically like such a cascading effect. And at some point, these very dense stellar objects collide. And when they collide, there will be a gigantic explosion, which is called a kilonova, which you can see here. And it's one of the most energetic events we can see in the universe. And it really forms the densest objects we can see in the universe. And we have seen these things. I guess you all are aware of LIGO and the LIGO observations in the past decade. In 2017, there was the first detection of such a system. And so this is pretty cool. And so if we ask ourselves, what actually stabilizes neutron stars? These are so dense objects, right? If we look at a regular star, so here's a main sequence star like our sun, we know that usually gravity wants to collapse the star because gravity does these things. And there needs to be some outward force, something that exerts pressure to stop the star from collapsing. And in the main sequence star, that's fusion, right? Nuclei fuse, they release energy, they heat up the matter, and this thermal pressure pushes against the gravity. And so at some point, there's an equilibrium, and the star is stable and just burns. And once the fusion stops, it collapses. And when it collapses, it can become a white dwarf. maybe most of you have heard, our sun will become a white dwarf. Basically, a white dwarf is a system that is stabilized by the degeneracy pressure of electrons. So you have electrons in the system. You increase the density. At some points, the electrons don't want to be close to each other, and they exert some degeneracy pressure. But what stabilizes neutron stars? If you think of neutron stars, I told you they have a mass of the order of the mass of our sun, so that's 10 to the 30 kilograms, in a radius of 10 to 13 kilometers. And if you calculate the average density, it's like 10 to the 14 grams per cubic centimeter, which is quite high. If you compare this to an atomic nucleus, such as lead-208, it's much smaller, it's much lighter, but if you calculate the average densities, it's also 10 to the 14 grams per cubic centimeter. And so this is called the nuclear saturation density. I will talk about this more later on. But the densities in the neutron star are comparable to the densities in an atomic nucleus. And so the interactions that stabilize an atomic nucleus are also the interactions that stabilize a neutron star. And so it's nuclear interactions that we need to know about to understand what a neutron star does and why it does the things it does. Okay, so there's another interesting thing related to neutron stars, actually, which is that I told you there's this kilonova explosion. And basically, the kilonova explosion is a result of nuclear synthesis. So here you see the nuclear chart, the number of protons versus the number of neutrons. And that's a bit older, but maybe not that much changed. So in black, you see the stable atomic nuclei that we know. And then in green, we know there's the unstable atomic nuclei that we know. And then these are the drip lines. So these are the limits of nuclear existence. And there are, on the neutron-rich side, there are two important nuclear synthesis processes. There's the S process, the slow neutron capture process, which is happening when usually the neutron density is very small. So you have a nucleus, it captures a neutron, and before this guy can capture another neutron, it decays. And then it captures another neutron, decays, and goes on and on. If you have a lot of neutrons, many, many neutrons, you can do the rapid neutron capture process. So you capture a neutron, but before this one can decay, you capture another neutron, and you capture another neutron, and so on and so forth. And so you can really go all the way out here to these drip lines, and you have many neutrons. And there's one system where we have really many neutrons, and that's a neutron star. And if you look at a neutron star, so here's a simulation that comes from Los Alamos using the Skynet code. And you see here, there are many neutrons. So basically, you see the nuclear chart again, and there's the abundance of particles. There are very many neutrons. And then there's some seed nuclei. They come usually from the crust of neutron stars, and we will talk more about this later. But then, if you have your neutron star merger, these guys capture neutrons. And you see that slowly, they really build up all these neutron-rich nuclei. And they form this line. This is the neutron drip line. They cannot go beyond that. But they build up all these atomic nuclei out up there. And at some point, the neutron exposure stops. These things decay back to the valley of stability. And while they decay, they emit light, and that's what we see as a kilonova. And this, goes on and on. So if we want to understand nuclear synthesis, or the structure of atomic nuclei more generally, or we want to understand the reactions among the nuclei and nucleons, and we want to understand objects like neutron stars, we need to understand the interactions between the particles that make up these systems, so mostly neutrons, or neutrons and some protons. And so this is a very old problem, actually. We know, in 1896, radioactivity was discovered by Becquerel. And then after a lot of work by Rutherford and the Curies, in 1911, it was proposed that the mass of an atom is actually, or the majority of the mass is in an atomic nucleus, right? And then in 1920, Rutherford suggested that the proton is the source of the positive charge. And then in 1932, Chadwick discovered the neutron. So we knew that there is a nucleus, and we know there are protons and neutrons. But the question is, why would this thing not just fall apart? Why? Because protons are positively charged, right? So why would the atomic nucleus not fall apart? And actually, in 1932, there was the first proposal that actually neutrons are just like protons and electrons, very tightly bound, and there's an exchange interaction between them where the electron is the exchange particle. This was proposed by Heisenberg. But then actually in 1935, there was the first proposal that actually is still true, and this describes the truth about nuclear interactions. This was made by Hideki Yukawa. And basically, he came up with a potential of this, this form. So the potential of the force between the neutron and the proton should not be of Coulomb type, so not very long range, but it should decrease more rapidly with distance, and it can be expressed as this, which is actually still the correct form. And then, thinking about the range of the nuclear interaction that was known by then, based on the range of the atomic nucleus, he deduced that the exchange particle should be around 200 times the mass of an electron. And so it's around 100 MeV, right? 200 times the mass of an electron. And he didn't know there was a pion. Later, people found the pion, and the pion is actually this exchange particle that he found. So he predicted something that was called a meson, because it's between electrons and between nucleons, right? So it's a middle mass particle. And as I said, this is the pion. This interaction is the one-pion exchange interaction, and it's still one of the most important contributions to the nuclear force. And I think this is a great example for theoretical reasoning describing experimental data and predicting things that experiment hasn't yet seen. So I think this is really cool. Okay. Are there any questions so far? If not, I will proceed. So, if we want to understand nuclear interactions, we actually would need to understand the fundamental theory of strong interactions, which is quantum chromodynamics. So here you see a picture of the standard model. I guess all of you are very familiar with this. And you see we have quarks. There are 6 species of quarks. Then we have leptons, so electrons, muons, tauons, and the corresponding neutrinos. There are the bosons of these interactions. The gluon is the exchange boson of the strong interaction, so it interacts between these quarks. The photon of the electromagnetic interaction, and the Z and W boson mediate the weak nuclear force, or like beta decay and things like this. So the quark model was proposed in 1964 by Murray Gell-Mann. And basically, what we know is that here you see some properties of these quarks, right? So you see masses, the charges that they have, the spins that they have. And you see there are actually 2 very light quarks, the up quark and the down quark, and then there's a little bit heavier quark, which is the strange quark, and then there are 3 much heavier quarks, right? So most of nuclear physics actually only is interested in these 2, the up and the down quark. But all of these particles, in addition to these quantities, charge, spin, and so on, they carry a color charge, and the QCD predicts that composite particles of quarks need to be color neutral, so there are 2 types of particles we can form. We can have baryons. They have 3 quarks, each of them carrying a different color, and then the system is color neutral. And such a baryon, an example for baryons are the neutrons that we're all interested in. And then there are mesons, which are a quark and an antiquark carrying a color and an anti-color. And for example, these are the pions. And then there is a Lagrangian you can write down for QCD using the 3 lightest quarks, and it looks like this. And basically what it just means is there's a kinetic part for the quarks up here. So basically, there are the quark fields. Then there's this. This is the gluon vector, so the quarks can interact with gluons, and the gluons can self-interact. But you don't have to understand this in detail. It's just, I think, good to understand that basically this is a very simple Lagrangian that describes how these quarks have kinetic energy and interact with gluons. And via gluons, they can interact with other quarks, and that's everything it says. So it looks extremely simple, but we cannot solve it. So it's not that simple. Things that look simple don't always have to be simple. If you use QCD, you can write down the phase diagram, so you can look at the theory and see what are the different phases of the matter given different thermodynamic properties. So there's the temperature on one axis here, and there's baryon density or chemical potential or whatever you want on the x-axis. And if we're at low temperatures and low density, this is where we live. So we live here, so we live down there. But nuclei live here, so they have a certain density. And at these densities, quarks are building these hadrons, so baryons and mesons, what I just showed before. But if we increase either the density or the temperature or both, quarks and gluons can become free and form a soup of quarks. And we don't really know where this transition happens. We can probe it experimentally at different machines like RIG or the LHC or FAIR in Germany. at some point when it turns online, or FRIP in the United States. We can also try to probe this axis with neutron stars, because as I told you, they are very dense objects, so they probe this density axis. And so we might understand more about this. But generally, we don't really know where any of these lines is. The only thing we really do know is that nuclei or quarks are composite particles at low densities, because we can probe them experimentally. But so obviously, we would like to understand this better. Okay, then if you have these quarks, you can build particles, and I just wanted to show this briefly because what you see here along the y-axis is how many strange quarks there are in the system, and then along these diagonals, it's basically the composition, like how many up or down quarks you have. So it's only really just the 3 lightest quarks, and you can build these many particles out of those. And then basically along these axes, it's the charge. So if you have an up, like if you have on the left side, you have meson, so you can have a quark and an anti-quark. And then you see if you have 0 charge, you can form these particles. But if you also want to not have strange quarks, you will be here along the pion axis. And then you have basically, you have 3 pions, the neutral pion, the negatively charged pion, and the positively charged pion. And on the other side, it's basically the same. You can increase the strangeness content, or you have up versus down, how many ups and downs you have. But then 0 strange quarks. If you only use up and down quarks, you can build the neutron and the proton. And these are exactly the particles that I will focus on. All the others I don't care about. They might be in neutron stars, I don't know. But I will not discuss them here. So, very boring, but still complicated enough. So yeah, I will only focus on these guys, the up and the down quark. Okay, so if you use quarks, I told you Yukawa found the 1 pion exchange, right? So 2 nucleons do something and exchange a pion. In the quark picture, it looks actually something like this. So your proton consists now of 3 quarks. They have color charge. The neutron that it interacts with consists of 3 quarks, has other color charge, and then they exchange this meson, which is the pion. But if you really zoomed in on this, if you had the best microscope in the world, highest energy, you would see something like this. It would actually be more complicated like this, but you would see something like this. So if we want to understand nuclear physics, how protons and neutrons interact, we need to understand something about the physics of quarks and what they do. And I'm sorry, because I think this is very important, but it's also the most complicated thing I will talk about, which is chiral symmetry. Which is one symmetry that I don't know, who of you has heard about chiral symmetry? Okay, that's good. You should explain it. Perfect. So if you look at this very, very simple Lagrangian that describes the QCD interaction, if you set the masses to 0 and you ignore the gluons for now, if you only focus on the kinetic term, you can you can split it in and project it on left and right-handed quarks. So chirality is like if the spin is aligned with the momentum of the quark or anti-aligned. So is the rotation left-handed or right-handed? So that's why I write this, and basically the symmetry is called chirality, which is where this comes from. Okay, so if you do this, if you decompose the kinetic term, you find something like this, and you see that you have left-handed and right-handed quarks, they split completely, and so you can rotate them independently. You would still get the same physics of the system. So if the properties of the system don't change by applying some rotation or some transformation, you have a symmetry, and this is chiral symmetry. So the independent rotation of the left and right-handed quarks. And so you can rewrite this actually into an isospin symmetry and a parity symmetry, but basically this would be chiral symmetry. Now, what does this mean? So, for example, if you define, I told you you can rewrite this in isospin and parity symmetry, so let's look at the isospin symmetry. So you can define an isospin operator, which is basically, it's given like this, and these taus are Pauli matrices. And then you can say the up and down quark are actually one particle with 2 isospin states. Like you have a spin-up neutron and a spin-down neutron. You can have a spin-up light quark and a spin-down light quark, and this would be the up and the down quark. So they both have isospin 1/2, but their isospin projection is different. And so this isospin, and basically they are almost equal mass, right? So it looks pretty good. You can use this and look at the baryons that are made of ups and down quarks, and this symmetry carries over to them. So if you look at the nucleons, they have spin 1/2, no orbital momentum, so total angular momentum is 1/2. They have isospin 1/2 and even parity. And so you write down the proton and the neutron. They have now the two different isospin projections, but the same isospin 1/2. And their masses are very, very similar. 938.272 MeV versus 939.565 MeV. So very similar. And so you can say isospin symmetry is almost exact. It's not 100% exact, but it's almost exact. And that's great. And it's not 100% exact. OK, sorry, before I get there. So if you look at this other part of chiral symmetry, right, what happens under parity transformation? If you look at nucleons, the systems with the even parity, it's the proton and the neutron, I just mentioned this. If you look at the systems with the odd parity, they are much heavier. They're almost, not twice as heavy, but they are considerably different in mass. And so this symmetry is not there in nature, right? We do not see this. So chiral symmetry must be broken, and we can just infer this from looking at masses of particles. So why is this the case? So the first thing is, if you look at the mass term breaks chiral symmetry explicitly. You cannot really split it into independent terms for left and right-handed quarks. The mass term couples these quarks, and so based on the masses of quarks alone, chiral symmetry cannot be there in nature. But the masses are so small that the explicit breaking of chiral symmetry is only small. And so this is why the isospin symmetry is almost exact, because masses of quarks are generally small. However, chiral symmetry is also spontaneously broken. So who of you knows about spontaneous symmetry breaking? OK, perfect. So this is not the surface of the QCD Lagrangian, obviously. It would be much more complicated. But this is like a sketch. If you have a symmetry in the system, so the symmetry axis would be this z-axis, right, this dashed thing. So here, the ground state is on the symmetry axis. So if you're in the ground state of the system, you have a symmetry, right? You can rotate. It will always look the same. However, the QCD Lagrangian doesn't look like this. Schematically, it's shaped like this. So the symmetric state is not the ground state of the system. The ground state breaks the symmetry spontaneously. So if you have your system in this symmetric state, it would decay into the ground state. And so now, when you rotate, you get a different system. So chiral symmetry is spontaneously broken just by the nature of the QCD Lagrangian. And so this actually has important consequences. First of all, it explains why the nucleons with odd and even parity do not carry the same mass. And the other consequence that is important, and this is why I go through all of this, is that if you have a spontaneously broken symmetry in nature, there's the Goldstone theorem that says there's a massless excitation. Basically, something that would rotate you around here costs no energy, right? You can just move the system over there. Doesn't really matter, costs no energy. So there has to be some excitation around the ground state of the system. So Goldstone's theorem predicts this, and this excitation is the pion, so the exchange particle that we talked about before. And it's not exactly massless because we have also its explicit symmetry breaking because quarks actually do have mass. But it's much, much lighter than any other meson you would see, right? I mean, the next heavier meson, the rho meson or so, it's like 700 MeV, or even a bit larger. So the pion is really much, much lighter than any other meson. And so it's a pseudo-Goldstone boson. It's not a massless excitation, but it's a nearly massless excitation. And the other consequence of all of this is that pions couple to momentum, which will be important later. OK, so in everything I'm going to talk about, I will not use the quark picture. So here, that's the helium-4 atom. Let's ignore the shell and just focus on the nucleus. So I will not describe, or the goal of Ab-initio nuclear theory is not, depending on who you ask, the goal is not to describe the system in terms of quark degrees of freedom and their gluon exchanges and so on and so forth, because it's extremely complicated to solve. But we just assume that we're at low energies and low densities where quarks are confined to neutrons and protons. And then our interactions are between these particles. So we choose effective particles, basically. But the way these particles interact is still dictated by the symmetries of the fundamental theory. So your interactions cannot violate any symmetry that nature gives you. And these symmetries come from QCD. So that's the Ab-initio approach that I will talk about in the following, describing everything in terms of neutrons and protons. And I should also, by the way, say, I was charged to talk about the Ab-initio approach. I would like to call it microscopic approach in the following, because Ab-initio means from first principles, and people who actually do describe everything in terms of quarks and gluons would be reacting allergically to me calling this Ab-initio, because they think Ab-initio has to come from the fundamental theory. So some people will use Ab-initio, some people will use microscopic, it doesn't really matter, but what it means is we use nucleon degrees of freedom and describe their interaction. Are there any questions up to here? Sure. Okay. Oh, yes, I talk about this later, yes. But yeah, you do. Yes. Well, yes. I will get back to this. I talk about this
Ingo,
later.
can you please rephrase his question, because I forgot to give him the...
Okay. Do we have a micro? Okay, fine. The question was if you have antisymmetric wave functions, if you would exchange the particles, would you have to exchange isospin, basically? Yes. So I will talk about this later. Or I will get back to this question later. Any other question from a student? If not, I shall proceed. Okay, so I told you we focus on neutrons and protons, and that's not my mouse. Okay, so I will only focus on neutrons for the most part because they are most interesting, obviously, because they form neutron stars. And so if you, let's say you take a snapshot and you have a soup of neutrons and they do something. I told you they will have some interaction, right? There can be interactions between 2 neutrons and between 3 neutrons or whatever. But generally, if we write down these interactions, we can write down a Hamiltonian. That's this guy. And then we just solve the Schrödinger equation to get the energy of the system. That's everything we need to do. And once we do this, we have the wave functions, we have the energies, we can describe everything we want. So the thing that we really need is this Hamiltonian. And the Hamiltonian has to include, okay, obviously a kinetic part for all these particles. There are 2-body interactions, 3-body interactions. It all has to go into this Hamiltonian. Once we have the Hamiltonian, if I just gave you a Hamiltonian and told you solve this equation, this is a very complicated problem, and many people dedicate their whole career to writing computational frameworks that actually do this solution. So we need some computational method to solve this many-body Schrödinger equation. There are many, many methods. I will not talk about them, but I do something that I will do quite a lot during these lectures. I will refer to Francesca. So she will talk more about this. I will really just focus on the interactions, and that's it. If you want, maybe I have 1 or 2 slides on something else, but if you want to learn more about how you solve this many-body problem, especially in atomic nuclei, Francesca will talk about this. So, yes, let's talk about the Hamiltonian instead. So, we have to write down some nuclear potential, and we don't really know how this looks, right? We need some theory that tells us how this looks. And I told you, Yukawa proposed that there is a pion exchange, so we know something, maybe there is a component like this, but generally we don't know how the interaction should look. But we know its symmetries because we know the symmetries of QCD, right? So first of all, the potential has to be Hermitian because the Hamiltonian is Hermitian. It has to be symmetric under the perturbation of particles. So if you have a neutron interacting with a proton and you just flip them around, you still have the same interaction, right? It's translationally or rotationally invariant. So if you measure the interaction between the neutron and the proton here or here, it's the same. And if you rotate the system, it still stays the same. It's invariant under translations in time, and yeah, well, obviously, if we measure interaction now or tomorrow, it should still be the same system. Or it should still have the same properties. It's Lorentz invariant or Galilean invariant, so in an accelerated system, it's still the same. If you look at it in the mirror, it's still the same, so it is invariant under parenty and time reversal symmetries. It has to conserve baryon and lepton number, and these things are what I talked about before. It has to obey chiral symmetry. So interactions have to be almost isospin symmetric. So if you have 2 neutrons or 2 protons, or a neutron and a proton, or 2 protons in the same states interacting, it looks almost the same. And we have chiral symmetry. So there are pions, and pions interact in a certain way dictated by chiral symmetry. So whatever we do, it has to follow these symmetries. And so, so let's say we have two neutrons, let's say. Which quantities do you think the potential could depend on? What do you think?
We need to bring some candles to stimulate the students.
Sure. Everybody who answers, I will buy a beer. You can also just scream. I will repeat what you say. You can guess. It's fine. Very good. Spin. What else? Yeah, okay, you get a beer. Very good. But what else? That's very good. Actually, okay, yeah, that's very good. Anything else? Okay, very good. Okay, then spins we had already. Okay, so it can depend on the momenta. So that was mentioned already. Actually, you could think of it also as locations, right? So not only momenta, also locations, the spins of the particles, and actually the isospins of the particles. So okay, I kind of said it's two neutrons, but it could have still two isospin projections, or you could generally think it could be a neutron and a proton. So these quantities it can depend on, but then you already anticipated my next question, which is which are the combinations of these. If you look at the symmetries, it cannot depend on R1. It cannot, because then it would be not translational invariant, right? Because if you move a particle from its location to another location, R1 changes, and that would be bad. So it can only depend on the relative distance of two particles. The same is true with momenta. If it would only depend on one momentum, it would break the symmetries of QCD, so it can only depend on relative momenta. Spins, it cannot really depend on one spin alone, because if we reversed time, it would look the particle spins the other way around, so the interaction would not be the other way around. So it has to be a scalar in spin, a number in spin, and so it can only depend on this scalar product. The same is true for isospin. And then you have these very fancy combinations like spin orbit and angular momentum squared and whatever. But these combinations all come from the underlying symmetries. So we know these are the symmetries dictate us how we can basically put these guys together to form nuclear interactions. And so I wanted to give one example. So if you look at these pions, so now you see you can redefine these relative momenta, and then you can change the momentum scales, and I can explain to you later why you can do this. But basically, if you focus on Q, Q is the relative momentum between the relative momenta. And so it's basically the exchange, the momentum exchange of the particles that come in and go out. You can show this, but anyways. So if you look at the one pion exchange, we know that when it interacts, it should be proportional to this momentum. So this is what chiral symmetry dictates. It couples to the spin of the particle. It has an isospin component, and this comes from the fact that we have 3 different pions. So if you have 2 neutrons, you can only exchange a neutral pion. If you have a neutron and a proton, you can exchange a charged pion. And so this is why it has to be dependent on the isospin. And then there's this coupling constant, Ga. And so if we have the one pion exchange that looks something like this, we have 2 of these on either side, and then basically we get this interaction. So it depends on a scalar of isospin. It depends on something that looks more complicated, but it is basically momentum squared, right? It has also 2 spins. It cannot only have 1 spin. And then this is the propagator of the pion, because it lives in between. And then you can use the wavelength of the pion to estimate the range of the interaction by basically using h bar c over the mass of the pion. And h bar c is roughly 200 MeV Fermi, so dividing it by the mass, you end up with 1.4 Fermi for the range of the nuclear interaction. And that's basically the other way around what Yukawa used to determine what the mass of the pion is. That he didn't know what the pion, but okay. Very good. And so if you think about more, so I told you about the pion exchange, but imagine this is a very, very heavy meson. If you have a very heavy meson and you look at this propagator of this meson, and momenta are low because we look at low momentum nuclear interactions, basically this can be approximated as just a number, which is 1 over the mass. And basically this meson exchange becomes a contact interaction. And if you write down operators for these contact interactions, you find something like this. So you can have momentum independent ones. depend on these spin quantities and the isospin scalar product. You can have momentum-dependent interactions, so you can write down all of this. But generally, you have things that describe some contact interactions, and you have the pion exchanges that you've seen before, or that I showed before. Okay. So, as I told you, we don't know a priori what operators we should include, right? But we can derive some of these operators based on the symmetries. But we need to somehow, if we want to understand how the nuclear interaction looks like, right, we need to have some data to compare it to and to infer the properties of these operators and their strengths and so on and so forth. And basically, what we mostly use is two-body scattering. So we use two nuclei, we scatter them, and then basically we use this to constrain the interactions. And I wanted to introduce this. So I do not want to give a full recap of quantum mechanical scattering, because I think you all have heard this at some point. But there's a little refresher. So we have like let's say there's a nucleon down here in the center, and one nucleon comes in. And they interact using the nuclear interaction. And then you have one particle being scattered off. So if we write this, there's an incoming plane wave, right? This is this one. And then there's an outgoing spherical wave, which has this scattering amplitude in front of it. And the scattering amplitude basically contains all the information of the scattering process and is related to the cross-section. And it can depend on the angle and so on and so forth. And it can depend on the energies and whatnot. So basically, yeah. And basically, the cross-section is what we measure in the lab. So we need to somehow connect nuclear interactions to this guy, and then by comparing to the cross-sections, right, we could determine or try to determine nuclear interactions. Okay, so now the incoming plane wave we can expand in Legendre polynomials and Bessel functions such as this. I mean, that's a well-known expansion. And then if we go to very, very large distances, so very far out here or very far out here or whatever, this basically can be described as a sine function, right? Something like this. So that's just the incoming partial wave, the incoming plane wave, sorry. So now if we look at the scattered wave, something happens down here. There's some potential, some Hamiltonian that describes the interaction between these particles. And let's just assume for now that this is a local interaction. So local meaning it only depends on the position where the interaction happens, so that's R. So we can write the Hamiltonian as the kinetic part plus this local part. And if this is the case, then everything is again rotationally symmetric. If it's rotationally symmetric and we write on the Schrödinger equation, we can, basically the whole thing commutes with the orbital angular momentum operator L. And then we can write this radial Schrödinger equation. So you have again the derivative coming from the kinetic energy. This thing is the radial part from the derivative that gives you some angular momentum, or this angular momentum term, and then there's the potential again. And then UL is the radial wave function. So that would be the Schrödinger equation in this case. And so if we look again at very, very far away from the scattering center, so we don't really care about the particulars of what's happening there. We just think there is one potential, it does something, but then something happens to the particle and we measure it out here, very far away from the scattering center. So we can look at the asymptotic wave function. For the asymptotic wave function, basically this whole thing simplifies because R becomes infinity. And then the radial wave function can be written as something like this. So it's again a sine function, but now, if you compare, it has this thing, the delta L, and that's called the phase shift. So this phase shift, basically, I mean, it's self-explanatory why it's called phase shift, right? It shifts the phase of the incoming partial wave when you go and look at the outgoing partial wave. But this phase shift can be related to the cross-section. So basically, the phase shift is related to the scattering amplitude. And so if we know the phase shift, we can get the cross-section of this whole system. And here, the phase shift is characterized by an orbital angular momentum L. And so we call this a partial wave. So a wave that has a certain quantum numbers, right? And here it would be L. So we would measure one phase shift for one L, and then basically that's one partial wave. And once we measure the phase shift, once we measure the cross-section, we can extract the phase shift, and this phase shift is related to the nuclear interaction. And how is it related? You have to solve this numerically. But here you see, what you see here is the following. So that's a very simple local interaction, right? It's V of R some strength times some exponential. Some Gaussian, sorry. Some Gaussian. And so when you see here 0, this means the LEC, the C here is 0. And so this would be the gray line. And gray line means there's no interaction, right? The incoming plane wave just goes out again, and so you have no interaction. And now if you do this, if you put C2 minus 1, you have an attractive interaction. If you put C2 1, you have a repulsive interaction. And so what you see here is that once you have an attractive interaction, you have a positive phase shift, right? You pull the wave into the scattering center. If you have a negative positive repulsive interaction, you push the wave out of the scattering center. And so this is basically what you see here. And if you increase the strength of the interaction, you see it even stronger. I don't know if you can go back and forth. You see if you, if you make the green line is always repulsive, so if you make it more repulsive, it moves out. And if you make the other one more attractive, it moves in. So basically, attractive potential means positive phase shift. Repulsive potential means negative phase shift. So if we measure phase shifts, we can understand the sign of the interaction, for example. Another question for you. So I told you we can define partial waves using the orbital angular momentum quantum number L, but what other quantum numbers do you think could be important? Any guesses? Okay, no beer. So
maybe now you have to offer 2 beers.
Yes. Oh no, no.
So this will be the organizer. 2 beers. Okay.
No, now you have to buy me a beer because you didn't answer. Anyways, okay. So as we said before, there are also spins and isospins right in the system. So basically, the total Hilbert space. Sorry, by the way, I noticed. I realized right now. So that's not the Hamiltonian. That's the Hilbert space. So if it's this one, it will be Hilbert space. If it's the regular H, it's the Hamiltonian. But please don't confuse those. So the total Hilbert space has a contribution of space, position space, or whatever, which is the quantum number of which is basically the L, the orbital angular momentum. Then there will be a spin space or subspace that describes the spins of the particles, and there's a subspace that describes the isospins of the particles. And so the wave function also has a component in position space, a component in spin space, and a component in isospin space. And so the quantum numbers have to describe all of these systems. So you have L, the orbital angular momentum, you have spin coming from the spin space, isospin from the isospin space, and then you can couple, obviously, these two, you all know this, you can couple them to the total angular momentum J. So these guys describe any partial wave in nuclear physics. And so now, if we want to construct a total wave function, it has to be antisymmetric. And so the product of all of these things has to be antisymmetric. So we could have, let's say, if we have, okay, let's go here. If we look at S wave, so L equals 0. L equals 0 is symmetric here in the isospin space. So depending, the product of the spin and the isospin would have to be antisymmetric, right? If we would be in P wave, where L equals 1, this guy is antisymmetric, and so the product of these two has to be symmetric. And so you can use this reasoning to understand which partial waves are actually existing for nuclear interactions. So that's my next question for you. If you would have L equals 0 and spin equals 0, what does the isospin and the total angular momentum look like? So we're just in this case, L equals 0, S equals 0. What is T and J? Any guesses? I don't have the microphone. Can you scream? Yes, that's very good. And T? Yes. So basically, you can puzzle these things together. and then you find the total partial waves. And we always write them in this spectral notation. I actually don't know where it comes from, except that it's from chemistry. But basically, you write total spin, L, and J. And then basically T you can infer from the symmetry properties, right? So if you have L equals 0 and S equals 0, you have one S0, and one S0 has total isospin 1. So it's a very important interaction for neutron-only systems. If you have L equals 0 and spin 1, the isospin has to be 0, and you get 3s1, which is basically the partial wave of the deuteron. And then for p wave, you have the same, right? You can do these things around. And so for neutrons, or what we talk about, these might be the most important partial waves. But generally, for nuclear interactions, all of these partial waves provide some information for us. And so basically, we can use the phase shifts in these different partial waves. And I'm sorry, there's no y-axis here, but it would be the phase shift, actually, in degrees. Actually, this is the y-axis label, so I don't know why it's up there, but anyways. You have the phase shift as a function of laboratory energy, right? And you get this data, and you can extract the phase shifts from this. And here you have a different partial wave. This is 3s1, the deuteron partial wave. And again, you get the phase shift as a function of energy. And so they look actually very similar. If you would plot them on top of each other, they would look somewhat similar. But at low energies, they are different. So 1s0, you cannot really see it, but there's a maximum here, and then it would go down to 0, whereas 3s1 would go up to 180 degrees. And this is because it has a bound state, and for phase shifts, there's this Levinson theorem that the phase shift at energy 0 is n times pi, where n is the number of bound states. So here it's 1 times pi, so 3s1 has one bound state, and we know this bound state to be the deuteron, which is the lightest atomic nucleus in the universe. Well, if you don't count the hydrogen nucleus, which is just the proton, but okay. The smallest bound system. But yeah, basically, if you see, you extract the data and you know something about nuclear interactions immediately, right? Because whatever you do, whatever you model, if you go back to what I had before, if you use this, you get, and you do this modeling, you get the wave function. With the wave function, you get the phase shift, and whatever you calculate has to describe this data. Okay, so here there are a few more phase shifts. So I have the p waves, because I only showed the s waves before, but I told you, for us, p waves are also important because neutrons like p waves. And neutrons don't live in 1p1 because of what I showed before, right? The isospin is not right for two neutrons to be able to interact in this partial wave. But if you look at this triplet p waves, 3p0, 3p1, and 3p2, this is one of the interaction channels for neutrons. And so to highlight how we can use the phase shifts to determine the strength of interactions, if you look at the central potential that I talked about, the contributions to the p waves would all look the same. But if you clearly look at the data, this cannot be true, right? I mean, the potential cannot be only central. Because if it was, as I said, if the potential in all of these waves would be the same, the phase shifts would be the same. So something else is missing. And so another important contribution to the nuclear forces that you can just deduce exists by looking at these phase shifts is the spin-orbit force. So there is the spin-orbit operator, and you can evaluate this, and you get this formula. And now if you evaluate it in individual partial waves, so this could be 3p0, 3p1, or 3p2, you plug this stuff in here, and you get these different quantities. So the spin-orbit force in 3p2, the operator would evaluate to something positive, whereas in these two, it would be negative. And so, as I told you, an attractive interaction has a positive phase shift. In 3p2, the phase shift is positive. This thing is 1, so the interaction, there has to be some negative constant times this operator that describes the interaction here. And then if you look at this, you have a negative constant times this operator, so this will now be a positive repulsive potential, and see the phase shift is negative. It's exactly what nature tells you. It's great. But looking at all of these triplet p waves, do you think the spin orbit is everything there is? Is this enough? Anyone? It's a yes-no question. Okay, it's not enough. And you can see this by the fact, if it was enough, this thing should be negative all the time too, because this one is negative everywhere. So this should be actually twice as strong and negative everywhere, but it's not. So something is missing. And so if you do it more generally, you can write the interaction into some part that depends on isospin and that is isospin independent. And then each of these terms you can split in other contributions, and usually we have the central term, a spin orbit term, and something called the tensor. And I do not want to talk about the tensor in great detail because it's actually very complicated, but this tensor operator we have seen already. It's coming from the pion exchange, or it's in the pion exchange, right? It's this momentum dotted into spin. That's the tensor operator. And this is actually also contributing in the p waves and makes the one partial wave look different than the others. So generally, all of these contributions we know just by looking at phase shifts have to be somehow in the nuclear interaction. And then all these prefactors are just momentum dependencies. So we have to somehow come up with those, and we can still do this by comparing with the data at different energies and so on. But just by looking at the partial waves, we can determine the operator structure of nuclear interactions. And yeah, so this is the most, let's say this is all the most general form that the nuclear potential can have. At least up to a certain quality of nuclear interaction, let's say. Okay, any questions up to here? Okay. Okay, so in the last part of the first part, I wanted to talk about phenomenological forces because I think it's a good introduction to what I will talk about after. So I will show examples, but I will mainly focus on one example. And there will be a lot of equations, and I apologize already, but I promise I do it for a reason. So, okay. So there's this phenomenological argon V18 interaction. That's a 2-nucleon force. It's one of the most precise phenomenological interactions that people have developed. And if you want to read more about this, you can read about it in this paper. It's from 1995, which actually I think is amazing. And I will talk more about this in the next slides. So generally, this potential has 3 contributions. There's an electromagnetic contribution that I will not really talk about, because let's say we're only interested in neutrons. This one is very small. Then there's a pion contribution, and this R is a short-range contribution. And so you can again, or what people did in this paper, they looked at this short-range contribution and they modeled this in terms of these operators. So there's a central term, there's a spin-orbit squared term, there's a tensor part, there's this, sorry, this is not spin-orbit, orbital angular momentum squared, tensor part, spin-orbit, and spin-orbit squared. They just wrote this down as an ansatz. And then each of these radial functions has like several contributions, and all of these things are unknowns that have to be adjusted. So they just wrote this down as an ansatz by using the same logic we did before and all the work that was done before them, but that these are the most general operators that we should use to describe these interactions. And then this short distance component is basically described in terms of these kernels, but generally their strength is adjusted by some quantities, I, P, Q, and R. And these exist for different, so NN means there are, or STNN, the subscript, means the different isospin and spin configurations you could have. So it's basically going through the partial waves, right? You can have 2 neutrons, neutron, proton, and they can have isospin 1 or 2 or 0 and spin 1 or 0. So you have 4 numbers for each of 4 I's, 4 P's, 4 Q's, and 4 R's. Yes, and so what they did is they fit these 16 numbers to phase shift data and the deuteron energy, and then they came up with this interaction. So what you see here is, again, the data are these points, and then the argon potential, there are 3 lines. There's 1 line for neutron and proton interaction, 1 line for proton and proton interaction, and 1 line for neutron and neutron interaction. But let's just focus on the neutron-neutron line. Okay, let's focus on the neutron-proton line. It's the solid, the darkest shaded solid one. And you see, it describes the data fantastic, right? In all of these partial waves. So basically, that's exactly what I mean. You look at the data, you make some ansatz for how the interaction looks like that is guided by your observations, and then you do a fit to this data, and you get the nuclear interaction. And you can then re-express this nuclear interaction in, it's called AV18 because you can re-express it into 18 operator channels. And so the first 14 operators are the ones we saw. So we have, just by looking at the symmetries, right, we can write down these operators. So it's combinations of the one we have seen. And basically, that's the most general thing you can do. And then there are some other operators that I do not really want. Oh, hope it's not for me. You have these other 4 operators. They break isospin dependence because it's not exact in nature, as I told you, right? It's almost exact, but it's not fully exact. So these first 14 operators would behave as if it is exact, but since it's not really exact, there needs to be some correction terms, and they are these other 4 operators. But yeah, we will see many of those later again. But I think it's still interesting to think about this. People wrote down something in the 90s, then they did a fit to a huge database of scattering data, and they came up with one of the most accurate potentials, and you can see this here. So, okay, I have not talked yet about 3-body forces. I will do this in the next chapter of my lecture. But there are other 3-body forces, and if you then use these argon V18 interactions with one of these 3-body forces, which is called Illinois 2, you can calculate light nuclei. And for all of these nuclei, you see 2-body forces plus 2-body and 3-body forces compared to experiment. And so in this case, which is the deuteron, you only have 2-body forces, and it was fit, so it does fantastically, of course. But then if you go to heavier systems, right, if you use these Hamiltonians, 2- and 3-body forces, you're basically on experiment all over the chart up to carbon-12. So what do you see here is that, first of all, phenomenological interactions are extremely successful for light nuclei, at least. This is what we can see here. And we need 3-body forces. So nucleon interactions are not just between 2 nucleons. There is another component between 3 nucleons at the same time. And you cannot describe this as pairwise interactions of 2 nucleon forces. There needs to be a true 3-body interaction, because otherwise, if you look at helium-4, right, you are far off if you only use 2-body forces. You need to have another component to the nuclear Hamiltonian. And that's the 3-body force. Okay, and then I just wanted to say there's also another phenomenological interaction that was quite successful, which is called the CD bond potential. It was developed by Ruprecht Machleit. And so basically it models the interaction in terms of different meson exchanges. So the pion exchange we saw already, but you could have other mesons, they get exchanged. You put this all together, you fit this to data, and you also get an excellent description of scattering data, like in all of these partial waves. The line is on top of the points, which means the potential describes the data. So you have all of these fantastic phenomenological interactions that do what that describe the scattering data, but they have shortcomings. There are problems with this approach. Because first of all, okay, I asked you before, which operators can you write down, right? And we had like relative distance, let's say. But you can have relative distance squared to the power of 3, 4, 5. There are infinitely many ways you can put the relative distance, or you can use this, right? Same for the momenta. There are infinitely many operator structures you can write down if you consider having operators appear to larger powers or something like this. So how do we know which operators are important? How did they know that L squared and L dot S squared are important? But let's say, why is L dot S squared more important than L cubed or something? How do we know which operators have to be where? Then we also have a lot of knowledge in this 2-nucleon force, because from the symmetries we can write down these operators, and it turns out that this is actually a very good approach. But if you look at 3-body forces, that I will talk more about later, but their operators are much more complicated. They are not that simple as for the 2-body force, because you have now a 3rd nucleon that needs to be considered. And then it's really difficult because, to write down how these interactions need to look. So there needs to be something more systematic, right? Something needs to tell us, if this is our 2-body force, how does the 3-body force look like and is consistent? And then, because also if you look at these 2- and 3-body forces that were developed phenomenologically, none of them can really describe all systems accurately. So they are great in atomic nuclei, but then they are bad for neutron stars. Or they are good for neutron stars, but then they have shortcomings for atomic nuclei. So there is something missing, and that's a problem. Without this systematic way of addressing these 2 points, as I said, we cannot really get which get information on which operators to include to a given precision. So then we do not know how to improve the models, and we cannot estimate uncertainties of our interactions. And everything that we calculate needs to be accompanied by some uncertainty estimate, right? A theoretical prediction is not just a line. It's a line with a band that tells us where did we make approximations or whatever. And we cannot do this for any of the phenomenological forces. So it's not the final answer. And this is where I want to start talking about chiral effective field theory, but I first ask you if you have any questions to the first part. Okay. Sure. Sure. Oh, there's a microphone. No, I think you.
The question is related to the Urbana potential.
Okay.
The Urbana potential are phenomenological nuclear potentials, and how are, I mean, if there are multiple ways to derive potentials, phenomenological potentials, in which way? I mean, Mach-Light consider different degrees of freedom of the theory, but if you start from only mesons, how it's possible to only adding different tensors and potentials, or other ways?
So the bond potential is just a two-body interaction, right? There are no three-body forces. And the same for AV18, right? But in AV18, for example, you have pion exchanges and two pion exchanges. So if you look into the short-range term, if you really go into the paper and look, then some of the terms are pion exchange squared, basically. So it's like a two-pion exchange. And this is the way how you could get with mesons three-body interactions, right? So, and I will talk about this in a little while, but if you have like a, sorry, let me make it bigger. So if these are your mesons, okay, I don't know this. That's better. So if you have your mesons, that would be a two-meson exchange. And you can put in any meson you want, right? But let's say we break this meson apart, and we just put this to a third nucleon. You have a three-nucleon force now. And it needs to be related to whatever happened in the two-meson exchange, because you still have the same vertex here, for example. But basically, only based on mesons, you can do something like this by just having diagrams of this sort. You can also model them again. So if you now say your meson is heavy, they will become contact interactions, right? Which is what the Urbana interaction has. But in principle, you could also do meson exchange to build three-body forces. Any other question? Okay. Cool. Sure. Mm-hmm. Mm-hmm.
But it looks, after all, you chiral created that, and this seems not so important.
No, it's very important, actually. So the tensor force is very important. I hope I didn't say it's not. The tensor force is extremely important in nuclear physics. I hope I didn't give off the impression it's not. It's very complicated to describe, though, which is why I didn't want to do it in detail. But the pion exchange it describes the long-range part of the nuclear interaction. So you cannot get phase shifts correct without the pion exchange, and the pion exchange is a tensor interaction. You cannot really get the deuteron properties without the tensor interaction, right? Because deuteron is two partial. The ground state of the deuteron has two partial waves that are coupled by the tensor interaction. Yeah, we could talk more about this later. But the tensor is very important. Not so much in neutron stars, though. So for what I will talk about, it's not so important. Okay. Any other thing? Cool. Good. So I told you about these shortcomings of phenomenological interactions, and chiral effective field theory is an approach to address these shortcomings. I mean, it was not developed with the goal of addressing these shortcomings, but it does address all of these shortcomings. So the general idea behind chiral effective field theory is that as I said, we want to have an approach that addresses these shortcomings. And it should be some description of nuclear interaction that depends on a few parameters. Just a few, not a large number of parameters we fit, but as few parameters as possible that we can adjust to data. And if we do this, let's say, to data in a certain, let's say, phase shifts, we want to predict other things and make robust predictions. So we don't want to fit all the data we have. We want to fit where it makes sense to fit and then make predictions with, of other. I'm out of, okay, no, I'm back. We want this framework to be systematically improvable. So, okay. So there needs to be some guidance that tells us how to make the interactions better. It needs to include two-body forces, obviously, because we have a lot of data on those. But as we have seen, we also need many nucleon forces, so 3 nucleon forces and so on and so forth. And we need to be able to quantify uncertainties in the calculations. So that's what we want. That's our wish list, basically, right? And CarLFT addresses this. So the first thing, some of these repeats now what I said before, but I still wanted to repeat it because I think it's kind of important. So first of all, if we look at some nucleus, right, we have neutrons and protons. They consist of quarks. But if we go and look at this at low energies, our wavelengths are large. We do not see the quark substructure, really, right? So in atomic nuclei, most of the momenta are maybe 100, 200 MeV, so of the order of the pion mass. The wavelength this corresponds to is, let's say, 1 Fermi, and the substructure for these quarks is relevant at much, much shorter distances. So again, we choose effective degrees of freedom, which are the nucleons. We do not have to really worry about the quarks, right? I talked about this before. But this is, I said I will talk about chirally effective field theory, so it's effective because it chooses effective degrees of freedom, which are the nucleons. Then, if we are at these low momenta of the order of the pion mass, if we look at, there's this tower of EFT or whatever, basically, and it's built on this resolution scale. So you have there are collective excitations of nuclei and so on and so forth. If you're going to the momenta, typical momenta of the nuclei, you resolve neutrons and protons in an atomic nucleus, right? And you can see their pion exchanges. And you need to go to much larger energy scales to actually become relevant to the quark substructure. So this is basically what this shows you. If you look at an atomic nucleus with increasing energy or increasing resolution, you will see different degrees of freedom. And this is like if you use a microscope, right? If you use an optical microscope, so low energy, you see certain things. If you use an electron microscope, much higher energy, much better resolution, you see much more details. And it's basically the same in every system, right? If you increase the energy that you use to probe a system, you see more details. But you see, there's a huge gap between this 140 MeV, that's like the typical momenta, and the scales necessary to look and see these quark substructures, right? So we resolve nucleons and we resolve the pion exchanges. But we have this separation of scales, right? This allows us to ignore all of these scales up there, or all of these things up there. And so the separation of scales is described by something that we call breakdown scale. So there is some scale somewhere between here, which we call lambda, which we call the breakdown scale, which tells us if we describe nuclei in terms of nucleons with their pion exchange interactions, at some point this theory will break down. At some point this is not enough, because if we increase the energy more and more, we would see quarks, right? And so if we see quarks, we cannot assume it's only neutrons and protons anymore. So there must be somewhere the scale, but the scale is somewhere between, somewhere in here, so it can be much larger than the momenta in atomic nuclei. And one actually finds that is of the order of 500 MeV, so it's basically close to the rho meson mass. But it's larger than the 140 MeV that nucleons usually carry in terms of momenta. So, yes? Yes. Okay, so for the sake of this, I'm in momentum space. If you translate this into coordinate space, yes, you're right. There's some size, like the short range contribution of the potential is model dependent. You cannot measure this, you cannot see this. And if I gave you a nucleon potential and I told you to you probe energies that are, let's say, 0.1 Fermi, you would see quark substructure now. So basically, you can think of this either in momentum space, so there's an energy scale, a momentum scale where your theory breaks down, or you think about it in coordinate space, there's a distance below which the interaction breaks down. So there's a duality between momentum and coordinate space. But since it's a momentum expansion here, I will use momentum space. Because, yeah. But I will actually talk more about what you just said later. Okay, so everything that is beyond this, let's say the row meson exchange, right? We do not resolve now. So if we have a row meson exchange, it looks like a contact interaction for us now because we don't resolve it. It's just two nucleons doing something. We don't see the details. Similarly, there might be other degrees of freedom like the delta. So you have the delta isobar, so a pion and nucleon, when they scatter, could excite a delta. We don't resolve this, so we put it in a constant, right? It's just a contact interaction, and it will be multiplied by some constant. So all this short distance physics that is above this breakdown is not really resolved, and so we can capture it in these low energy couplings, or LECs. And then these couplings should be natural, so they should be of order 1. So a coupling like this should not be much, much larger than 1. And so basically, this is the approach. And you can compare this to the multipole expansion. So if you have an arbitrary charge distribution, right? It's very, very complicated. If you wanted to do this, I don't know. If you have a charge distribution like this, an electromagnetic charge distribution, you can try to write on an analytic formula that describes this charge distribution. You can integrate it, and so on and so forth. But if you look at the potential at a very large distance, the first term will just be the charge over R, right? So this complicated substructure is absorbed into just the charge, the total charge. And then there will be a next term, which I think it's P over R squared, which is the dipole moment, if I remember correctly. It's the same, right? So now you probe at a little bit higher energy, so you need to make a correction for the fact that you only assume the charge. But still, you absorb the complicated physics into just 2 numbers. And that's the same idea here. You absorb the complicated physics into 2 numbers. Sorry, more numbers. Here 2, there many, many more. But that's the idea. And the long-range physics, so this pion exchange physics, which is extremely important, you include explicitly, because we resolve it. Okay, and if we do this, this will lead to a very systematic expansion of the underlying Lagrangian. So basically, you can just expand the Lagrangian in terms of momentum. Oh, I'm sorry. So I called this P before, now it's Q, but it's still a momentum. So momentum over breakdown scale times some function. And this function can depend on the momentum itself, and then these low energy couplings, GI. So that's a very general expansion. And then the Lagrangian should contain all the symmetries of QCD, right? So this effective Lagrangian has different contributions, pion interactions, pion nucleon, nucleon, nucleon interactions, but all of them have to somehow obey the symmetries of QCD. And I will actually focus on this part only, the nucleon-nucleon part. Then all unknown physics, everything that is happening up here, things that we do not model explicitly, is captured by these LECs. They have to be determined, and usually we use data, or I mean, that's the best approach. We fit them to data because data knows about all the physical processes that happened in the first place, right? If you do scattering, theoretically you cannot resolve this, but somehow it affects whatever happened in the experiment, right? So scattering knows about everything. Ground states of nuclei know about all the physical processes, so if you fit your LECs to experimental data, you absorb all of these effects in your LECs, ideally. Okay. Fine. Yeah. How much time do I have? How many minutes do you give me?
They gave you, I mean, up to 12. We started.
Okay.
5 minutes later.
5 minutes. That's good.
5 minutes is good.
I like that. Okay. So, so now I told you we need some systematic expansion. We need to somehow know which diagram appears where in our systematic expansion. And this is usually described by something called power counting. So there's a power counting scheme. And the most commonly used one is called Weinberg power counting, after Steven Weinberg. And basically the idea is we use an effective Lagrangian to calculate an effective potential, and then we expand this effective potential in powers of momentum or the pion mass. And then this gives us a potential like a V of R or whatever, V of momentum, whatever you want. And this is then what we use and plug into our many-body solvers, like what Francesca will talk about. And then I will talk about this tomorrow, I guess. We remove some divergences when we do this solution by introducing a cutoff. But yeah, I will talk about this tomorrow. Okay, and so then, yeah, this is the last thing I will talk about. So then, schematically, you can draw a picture of the nucleon potential as a function of distance. So it looks something like this. I told you already, at long distances, the interaction is determined by the one pion exchange. And this, this potential is basically the first part of the nuclear interaction we ever found, right? Because Yukawa predicted this, basically. Then at intermediate distances, there are things like 2 pion exchanges, 3 pion exchanges, and so on and so forth. And then the short distance physics we model by these contact interactions. So now what I want to say is this is very schematic, though. It's a schematic picture of the two-body interaction. The potential is not observable, and this is what we basically discussed before. This short distance physics here, below, let's say, half a fermi or so, it's not, it's, let's say, beyond this breakdown of the theory. We model the physics here as a short distance interaction, but we cannot really describe processes that happen on these short distances, right? We are interested in processes that probe the potential more at longer distances. So whatever we do here is model dependent. We can never measure the nuclear potential. We can just measure a nuclear potential given a certain scale or energy scale that we use to infer the potential. And I will actually have a slide tomorrow that shows you this mathematically, why that is the case. But okay, so we can model this type of potential using these different contributions. But then, as I said, I show here 3 diagrams. And all of these diagrams describe some process, right? As I said, 1 pion exchange, 2 pion exchange, contact interaction. But if I gave you pen and paper and asked you to write down more diagrams, you can do this infinitely long. There will be infinitely many diagrams you can ever write down. And so somehow we need to arrange those. So we need some systematic expansion. At leading order here, we know there's a pion exchange and there's this short distance physics. And then we know at next to leading order, there are corrections to the short distance physics. And then there are these 2 pion exchanges, for example. So they are less important than these 2 contributions. By the way, the difference between these guys, so this is short distance and this is short distance. But this is short distance that has no power of momentum, so it's momentum independent. This is short distance that is now proportional to momentum squared, so it carries different momentum dependence. Can anybody tell me why at NLO there is no Q over lambda to the power of 1? So why is NLO next to leading order momentum squared and not momentum 1? Correct, parity. Very good, thank you. So yeah, as we said before, we need to have even powers of momentum, right? Otherwise, we would violate parity symmetry. Very good. Okay, and then obviously we can go on and write down more diagrams. So after half an hour of you writing down diagrams, we can put them in here. And that next to leading order, which is now momentum cubed, there are more pion exchanges. So now you see here, this is the same diagram as there, except here something else happens in this vertex, right? So there's some sub-leading correction to this diagram appearing here. Similarly here, there are more contact interactions. There are now 3 pion exchanges, and so on and so forth. So you make these diagrams more and more complicated, but in a systematic way. In the same way, you see there are also 3 body forces. So we will talk more about those tomorrow. But there are 3 body forces, there are 4 body forces, and they all are connected in this systematic framework. And you obtain this hierarchy of nuclear forces. 2 body forces are more important than 3 body forces, are more important than 4 body forces, and so on and so forth. And so I guess I'm out of time, and we will talk more about this tomorrow. But are there any questions up to here?
We should allow some questions. This is important. Yes, Paul.
I've got a question about, like Galston theorem, spontaneous symmetry breaking versus like explicit symmetry breaking, because I'm familiar with the Galston theorem. Once you've got a given theory, you break like spontaneously. It's given symmetry. We have like both certain modes, right?
Yes.
But like, how do you see the difference like mathematically between like a spontaneous like broken symmetry and a explicit, as you wrote, broken symmetry? Because like, for example, when you show later like the argon 18 potential, like there are all these 18 operators, 14 operators plus these 4 that will break the symmetry. And so I was expecting to see the, like the explicit symmetry breaking term that will account for that.
Okay, very good. So the explicit symmetry breaking is there because quarks have finite mass, right?
Yeah.
So you see this by the fact that you assume the pion has a finite mass.
Yeah, okay.
So it's implicit because it's in the QCD Lagrangian, right? If you look at the QCD Lagrangian, you will not see spontaneous symmetry breaking, right?
Yeah,
Just by looking at the Lagrangian. But you see explicit symmetry breaking, and its consequence is that pions have mass, for example.
Like
so
in a given potential, then, like a phenomenological potential,
Yes.
like what does this correction term look like?
Okay, so these correction terms, maybe I can show them tomorrow. But these correction terms basically just account for the fact that if you look at 1 as 0, and everything I told you, right, neutron-proton and neutron-neutron scattering would look the same. But it does not, right? So there needs to be a component in the interaction that is proportional to the isospin projection, not just the total isospin. So NP and NN can have both isospin 1, but the projection would be different, right? NN is isospin projection plus 1, and NP would be 0. So there needs to be something that is dependent on tau z, basically, the isospin projection. And so these terms will look like this, basically.
Some other questions?
I have 2 questions. So first of all, at N2 allow, you have an odd power of momentum. How
Yes.
does this correspond to parity conservation?
Yes. Yes, it does actually. I will talk about this tomorrow. But what I can answer the question already now. So it's an expansion in potential and number of pion masses. So here you can construct something that basically has a pion derivative that gives you a pion mass, and this is why it's power cubed. Whereas if you did the same here, it would just be a number, and you would absorb it at leading order. So, but that's where it comes from. It's basically a pion derivative. Yes.
Okay, thank you. Then I have one more question. So you have this hierarchy of nuclear forces, and you also put some dots there for, in principle, I guess, 5 nucleon interactions.
Yes.
Do you not run into some problems at some point due to Pauli statistics that you cannot have more than?
Okay, that's system dependent, right? I mean, if you have, so let's say you have 3 neutrons. You have a neutron star. You have infinitely many neutrons. You cannot have this diagram because of Pauli principle.
Okay.
But in a system with neutrons and protons, you can have this. So now if you have 5 body interactions, if they are S-wave or whatever, you cannot have them in neutron matter. But there will be a system, or there will be some operator structure that basically describes, you can have 5 neutrons together, they just have to be in a different quantum state, right? So there will be some interaction that captures this. So this depends on the system you study. And some of these interactions, not all of these contribute to all systems at a given order. But there will be some 3-body forces that contribute in pure neutron matter. There will be some 5-body forces that contribute in pure neutron matter at some point. Okay. But obviously you don't want to go there.
Thank you.
Okay, one more question.
You have to ask, or we can't go to lunch.
Yes, it's time to go to lunch. So remind you, 1:30 here we start. So thank you, the 2 speakers of today. The information about the restaurants, there is a QR code that you can see close to the secretary. You just put your telephone there. There are the suggestions of the restaurants, okay? And, but the voucher is can be used only in 2 of them, okay? The cantina here and the other one that I mentioned. Okay, obrigado.